For our last class, we'll just finish up with a few more things about Turing machines. So recall that in the last one, we proved that ATM is not inside of sigma 0, but it is inside of sigma 1, and that not ATM is not inside of sigma 1, but it is inside of all. We also proved that there are an infinite number of other things that are not inside of sigma 1, because we proved that the size of sigma 1 is smaller than the size of all, and in fact infinitely so because they're both infinitely large. So what we're going to do next is we're going to talk about a number of other problems that we know are also not in sigma 0 or in sigma 1 that are also useful. Basically, we want to say that, like, okay, well, yes, there are an infinite number of them, but what about some like practical useful things? And we're going to use a technique that's called reducibility. There are many applications of reducibility. We often use reducibility when we're talking about complexity classes, but in this case, we're going to be talking about it just in terms of language categories. So reducibility is the following idea. We say that A is reducible to B, which we write as an A less than MB. The M stands for mapping. It is mapping reducible to B if there exists an F which is a computable function. And remember, computable functions are Turing machines that are in sigma 0, where for all W is inside of A if and only if f of W is inside of B. So what's the idea behind this? The idea behind this is that A is some problem that we would like to solve. It's some program that we want to run. And what F does is it takes that program, that problem, and compiles it into another form that we then solve with B. So here's an example. Imagine that we want to be able to solve decimal arithmetic, and that is A. So A would be decimal arithmetic. B would be something like binary arithmetic. Okay, so I have a computer here that can do binary arithmetic, but what I really care about is doing decimal arithmetic. So I would like to be able to write 23 plus 17 equals something. What is it supposed to equal? It's supposed to equal 40, okay? And I want to be able to convert that problem into a binary problem, okay? So I'm an idiot, so I'm going to like open up my little calculator so I can figure out what these things are in binary, because I don't know off the top of my head. All right, so we want 23. Okay, so 23 would be 0. Oh, sorry, not 0. It would be 1, 0, 1, 1, 1 plus. Then we want 17. Oh, clear 17. Okay, so that is 1, 0, 0, 0, 1, and we want that to be equal to 40. And what's 40? 40 is 1, 0, 1, 0, 0, 0. Okay? So f is the function that takes this problem and returns that problem. So it takes this string right here that does decimal arithmetic and turns it into that one that does binary arithmetic. If I can write such a function, f, then that means that A is mapping reducible to B. Because if you gave me a binary arithmetic solver, I could use that to make a decimal arithmetic solver by first taking every decimal arithmetic problem, translating it into binary, and then being good to go. Okay, so that's what mapping reducible means. Now, mapping reducible is very useful because mapping reducibility preserves the computability of something. Specifically, what we mean is that if A is mapping reducible to B, and B is inside of sigma 0, then that means that A is inside of sigma 0. So if B is a problem that's decidable, and we have a computable function that takes an A problem and turns it into a B problem, then that means that A is also decidable. Similarly, it's the case if one is inside of sigma 1, then the other is inside of sigma 1. Okay? But also more interestingly, something that we know is that if A is mapping reducible to B, and we know that A is not inside of sigma 0, then that tells us that B must not be inside of sigma 0 either, or correspondingly sigma 1. Okay? So how is that useful? That's useful because we can prove that for all B, if ATM is mapping reducible to B, then that implies that B is not inside of sigma 0, and not B is not inside of sigma 1. Okay, so every time we show that something is mapping reducible to B, that tells us that that thing is also not decidable, and its complement is not computable. So let's look at an example of this. An example problem would be called ETM. So what is ETM? M, the encoded version of M, is inside of ETM if and only if M is a Turing machine and the language of M is empty. So this is very similar to what we can do on DFAs, where we can look at a DFA and we can figure out if there's any string that would be accepted. So if something like that were possible for Turing machines, we'd be able to know that it wasn't empty. So what we want to do is we want to prove the following theorem. We want to prove that ATM is mapping reducible to ETM. And that is the same as saying that there exists a function f such that if W is inside of ATM, if and only if f of W is inside of ETM. Okay, now what does that mean? W, in this case, is an M and a string X. And so W is an M and an X, and it is inside of ATM if and only if M accepts X. And what we want to do is we want to make FW return something that's inside of ETM. So that means that we want M to accept X if and only if some other machine, MPrime, its language is empty. Okay, so this is the setup of F. F has to construct an MPrime where the language of MPrime is empty if and only if M accepts X. Okay, so how can we do that? Well, here's what we do. We just say that MPrime takes in input Y, and what it does is it says, I'm going to run M on X. If it accepts, then we will reject Y. Otherwise, we're going to accept Y. Now notice that this machine right here is either completely empty or completely full. It's empty if M accepts X, and it's full if M rejects X. And so what we've now done is we've produced a machine MPrime where its language is empty if and only if M accepts X. So if you could imagine there being a machine that would solve the ETM problem, we could give it this program and it would tell us what was happening. Now let's translate this into something that would be useful in practice. Okay? Imagine you wrote a C program, and the C program returns a Boolean. It returns yes or no. So you have any complicated C program, some big giant C program. And you want to ask the question, does this C program always return false? Because maybe it's some really complicated program, right? And what you would like to do is you'd like to optimize it so that it becomes just return false. That would be really awesome if you could do that. However, you can't do that because what I could do is I could make a program that what it does is it takes as input something, and then it goes off and simulates a Turing machine. And then based on what that Turing machine does, then it comes back and returns true or false. Now the thing is that because any program that tried to optimize your program would have to be able to discover what the Turing machine would do, and we know that that's not possible, that means that you can't make this optimization. Okay, so this is an example of mapping reducibility. It allows us to expand the set of things that we know are not in sigma 0. Let's think about another problem that is interesting like that might be practical for us. So there's a problem that we call Reg TM. So M is inside of Reg TM if and only if M is a Turing machine and the language of M is inside of Reg. Okay, now what does this mean? Why would this be useful? What this does is it's going to take a description of a Turing machine and tell you whether or not there is an equivalent DFA that would solve the same thing. Now this would be a really remarkable program. This is a program where you type in a C program and it produces an optimized circuit that does exactly the same thing as your C program. That's awesome, right? Okay, but we can't do this. What we want to do is we want to write a function f that takes in mw and returns MPrime such that M accepts W if and only if MPrime, the language of MPrime, is inside of Reg. Okay, so how can we do that? Well, it's really easy. What we'll do is we'll say that MPrime of X is equal to run M on W. I realize I just made a mistake. Oh no, never mind. Yeah. Run MPrime on W, and if it accepts, then return yes. Okay, because we know that sigma star is regular. Okay, so this language right here is regular. So if M accepts W, then we return yes, therefore it's regular. Otherwise, we're going to check if X is inside of 0 to the n, 1 to the n. Okay? And this language we know is not regular. Therefore, this machine M prime is either regular or not regular based on what M does. Obviously, there's another problem, which is the CFL TM, that works exactly the same way, except rather than checking if it's in 0 to the n, 1 to the n, it checks if it's 0 to the n, 1 to the n, 0 to the n. Okay, now we go between something that's in CFL and something that is not in CFL. So what this tells us is that it's not possible for us to figure out if something is, we essentially can't ask any meaningful question about Turing machines. We can't figure out if they're empty, we can't categorize their languages. There's something called, I think it's called Rice's theorem, which says that basically any non-trivial property of Turing machines is undecidable. Now, we don't always show that something is mapping reducible we don't always show that ATM is mapping reducible. Sometimes we build a network of these things. So for example, we can prove that the problem EQ TM, so EQ TM takes as input M1 and M2, and if and only if the language of M1 is equal to the language of M2. Remember, we did this with DFAs. So what we're going to do is we're going to prove that ETM, right, is mapping reducible to EQ TM. So what that means is that we have to write a function that takes an M and returns an M1, M2, such that the language of M is empty if and only if the language of M1 is equal to the language of M2. Okay? And here's the way that this function works. The way that this function works is that f takes an input m, and it's going to return m, and then the Turing machine that accepts nothing. So that Turing machine is empty. So this is very easy. So basically, we check to see if these two things are equal, and if they're equal, that means that m must be empty, which is exactly what ETM is. Okay, so this means that EQTM is also not decidable. All right. Now, the last thing that I want to do, so we've now talked about reducibility. We've talked about a few other example problems that are not decidable. And in general, essentially all interesting properties about Turing machines are not decidable. And now, as we finally leave, I want to end with one last idea. So, Turing machines, we can't really run them because they require infinite tapes, and we don't have any infinite tapes. Instead, all of our computers have a finite amount of memory. And we could represent that finite amount of memory like a DFA, but the problem with a DFA, it is really inconvenient to imagine expressing your computation this way. The reason it's so inconvenient is that we have to imagine the entire state space as one opaque block. But what we often want to do is think about the memory of our computers as being divided up into cells that we can arbitrarily move around and look at. So what we can do instead is define something that's called a linear bounded automata. And a linear bounded automata, I mentioned this before, also called an LBA, is a Turing machine with no infinite tape. Essentially, the way that it works is that the definition of the Turing machine is exactly the same. Like, it has all the same pieces, Q, sigma, that's a weird looking sigma, gamma, Q0, delta that's the same, Q cross gamma, arrow Q cross gamma, arrow LR, and then it's got QA and QR. Okay, so all that's the same. However, a string is inside of the language of the LBA, which I'll write as a fancy L. If and only if we give it one blank, you start off in Q0, you get the string W, and then you get one blank. Okay? And then what we do is we make a little special rule that basically says that whenever you're going to look, whenever you try to move past a blank, then it doesn't move at all. And you can't add more stuff. So the idea here is that you're like fixed. You can tell when you've reached the end. That's totally fine. But you can't actually add more stuff after that. Now it turns out that all the problems that I've told you about, like I told you about the 0 to the n, 1 to the n, 0 to the n, we talked about W hash W, we talked about ADFA, all of those things, those are all LBAs. In fact, it's really hard to come up with a useful Turing machine that does something actually useful that's not also an LBA. And here's the interesting thing about LBAs. The corresponding problems for them are actually decidable. So the ALBA problem is inside of sigma 0. It's actually even an LBA. Now, and that's not just because that's not because there's some like that LBAs like can't loop. Of course they can loop. The thing though is that we can tell when they are looping. And why is that? Well, the reason that we can tell that they're looping is because some L, it is defined, right, as Q in sigma, in gamma, in Q0, right, in delta, QA, QR. So we should ask the question, how many configurations are possible? Okay, how many are possible? Well, if the input is W, then what can we have? Well, we can have the size of Q in the number of states. Okay, so that's where there's all the different states. And then the head can be in each one of the positions of the input. So we could be looking at any individual character. Okay, so this is how many states, this is how many head positions. Then every position inside of the character could have been changed to be a different character. And how many could it be? Well, it could have been any of the things in gamma, so we're going to have gamma to the size of W. That is the total number of configurations that are possible inside of an LBA. All right, so that number right there is the maximum time that an LBA can possibly run before it will give an answer. If it runs more steps than that, it has gone into an infinite loop, meaning that it has gone back to an earlier place. And this is a very concrete thing. Like, let's think about our actual LBA that we wrote for the W#W problem. I think we wrote it on like day 18. Yeah, on class 18. I'm just going to scroll back inside of my notes so I can see what it looked like, so I can just count how many states there were. I think there were like 9 states. I know that I talked about this just a bit ago. Okay, here we go, 9 states. So we got the start, the one on the left, the one after that. So 1, 2, 3, 4, 5, 6, 7, 8. Plus one for the reject. Okay, so there's 9 states. So that means that there would be 9. And then how many things in gamma are there? Well, there's 0, 1, the blank, the smiley face, and the hash. So there's 5 things. So that would be 5. Okay, so now let's imagine that you gave it a string that was, I don't know, 10 elements long. So you would get 9 times 10 times 5 to the 10. Okay, so that is some number. Let's look at what it is. It's 9 times 10 times 5 to the 10. Okay, oh, whoops, that's 5 to the 19. Okay, so that number is 878,906,250. Okay? So that is the total number of possible configurations there are when we run the W#W on a string that is 10 characters long. Okay? So that means that you could solve the LBA problem inside of sigma 0, because all you have to do is you run the thing, you simulate it. If it says yes, you say yes. If it says no, you say no. And then if it runs more than this many steps, you stop. That's very easy. And this is in fact always possible. However, something that is really cool, I think, is that there are other problems on LBAs that are still undecidable. Like one of my favorite ones of these, oh actually, hold on, let me just say one more thing about a LBA. All of your programs are LBAs. And that's because your computer has access to only a finite amount of memory. So that means that, you know, if you ever had your program in the exact same memory configuration again, you know it's going to behave exactly the same, so you know it's in an infinite loop. So you could do something like that. You could monitor a program and detect whether or not it was in an infinite loop by seeing if it got to an identical memory configurations. All right, but there are some problems that are still undecidable. For example, LBA is not inside of sigma 0. And the way that we can do that is we can show that A TM is mapping reducible to LBA. Okay, so what does that mean? That means that we're going to take as input an MW, okay, and we're going to return an MPrime, where M, a Turing machine, accepts W if and only if the language of MPrime, which is an LBA, is empty. Now, how does this thing work? The idea here is that MPrime, okay, MPrime takes as input x. And what it's going to do is it is going to check that x equals C0, C1, C2, Cn. So it's going to check that it is a sequence of these things where C0 is equal to epsilon m dot Q0, W being this string, and Cn equals something, which we'll write as U, and then m dot Qa, something V, and where Ci goes to Ci plus 1 by the Turing machine rules. Okay, so essentially what MPrime does is it is an LBA that takes as input a trace of what a Turing machine does. It verifies that the first configuration is the one that it's supposed to be, the start state. It verifies that the last one is getting to the accept state, and then what it does is it makes sure that every transition is valid by the Turing machine rules for M. So essentially, what MPrime does is it doesn't simulate the Turing machine. Instead, it checks to make sure that a simulation that you provide is accurate. All right. Now, why does this show that? Why does this show? Ooh, sorry. So why does this help? Well, the reason that it helps is that M accepts W if and only if this machine right here accepts something. So I think what we need to do is we need to so this is a little bit wrong because this thing right here will only will accept valid traces, which means that MPrime is empty when this thing is not accepted. So that means that we're actually showing that not ATM is mapping reducible to ELBA. So we'll say does not accept W. Okay. So it does not accept W when the language of this LBA is empty, because that means that there is no such trace that actually demonstrates that the thing is possible. Okay, and so that is actually a really cool thing because it tells us that ELBA is not inside. It's actually that. That it's not inside of even sigma 1. It's not inside of sigma 1. It's an uncomputable problem, which I think is just beautiful, right? Because it tells us that these LBA things, they can do a lot, and we can analyze. It would be very tempting to say, oh, well, LBAs, they're so simple, they're just like Turing machines, there's all the things that we really care about are LBAs, we can even solve ATM on them, but there's even things that we can't ask about those. So remember, this whole class has all been about helping you understand this picture right here. Okay, and I'm going to give the big summary of this class now. Okay, so we got our big box right here. Okay, so in this class, we say that all the problems that a computer could ever try to solve, we can represent as subsets of sigma star, where sigma is basically like binary, okay, and sigma star are strings, binary strings, and the power set of that are all subsets of them. So that means that all functions that return booleans are inside of this box right here. All plausible functions, all ways of dividing up strings into ones that we say yes to and ones that we say no to. Okay? And it's really easy to define the finite sets of those, like 0 and 1 and whatnot, because we can just write them all down. But as soon as we want to talk about infinite things that have some repeating pattern, like 0 star, 1 star, we can no longer use finite notation. We can't literally write everyone down. And so what we needed to do was we needed to define the regular languages and the tool of DFAs. And DFAs, of course, led to NFAs and regular expressions. Okay? Where DFAs are like a machine model and regular expressions are like a programming language. And now we could talk about infinite sets, and we could talk about very easily computing with them. However, we showed that even these had things that we couldn't define. In particular, they lack the ability to count. The only kind of patterns that we could have would be patterns that had like no matching behavior at all. There was no way to check something in one place and then guarantee that that same thing matched somewhere else. And so because of that, we discovered things that were not regular. And this led us to find the CFLs. And the CFLs had PDAs and context-free grammars, which were two different ways of defining these kinds of languages. But even these had things that we couldn't do. Essentially, they allowed us to count, but they only allowed us to count one time. So if we needed to count multiple times, like with 0 to the n, 1 to the n, 0 to the n, that was not possible. So we needed to define Turing machines. And so that gave us the language sigma 0, or sorry, the language category sigma 0, which were Turing machine deciders. And one of the things that was really cool about Turing machine deciders is that they actually not only include every single individual element of these, but there is a single Turing machine. Single Turing machine that captures all of the behavior as this entire category of reg. So that is the ADFA. And you built simulators for these in your project in this class. But there are even things that are not deciders, like the ATM problem, which is the thing that will simulate what a Turing machine will do. And these are the Turing machine recognizers. Okay? However, even these had things that were not possible, like ATM. And in fact, we showed that the difference between these is infinitely large. There are an arbitrary number of things outside of here that we'll never be able to do. So essentially, we've shown that things that you can physically write down are way down here. Things that you can write circuits for are here. Some things that you can write like schematic programs for that use stacks are here. Things that use infinite memory are right here, and there's kind of a subcategory of those called the linear bounded automatons that use a finite amount of memory, but the program is flexible in exactly how much that is. And then we can divide those into the ones that always say yes or no, and the ones that may loop forever. And yet there are still an infinite number of problems that no human will ever be able to solve, no matter what computational mechanism they use. I hope that you had fun doing this, and it was very nice being with you on this journey. Peace out.